Okay, we're going to look at derivatives of vector-valued functions so we can get to some real calculus and applications soon. All right, so in order to think about derivatives of vector-valued functions, as we've been doing with everything else, we're going to go back and think a little bit about the definition of derivative for real-valued functions. All right, so you might pause the video for a second here and see if you can recall what this definition looks like. If you can, it'll make it easier for you to learn the definition of derivative for vector-valued functions. Okay, so if you pause the video and try to write that down, then hopefully this is what you wrote. If f is defined on an open interval containing x equals a, then f prime of a is defined to be the limit as h approaches 0 of f of a plus h minus f of a all over h, provided this limit exists. And sometimes we think about defining the derivative for all values of x for which this exists, and so you might write this limit with x instead of a. So here I have the definition written just as a generic definition, the derivative of the function at all values of x for which that derivative exists. Okay, so we're going to just now transition to vector-valued functions and thinking a little bit about how that might be a little bit different. All right, so notationally, first of all, we're going to call our vector-valued function r instead of f. We want that to be defined at and all around our point that we're doing the derivative at. So we would say on an open interval containing, in this case, t equals a. And then I'm going to start by defining the derivative at t equals a. So we'll define r prime of a, and that is defined to be the limit as h approaches 0, really just the same as our definition of a real valued function, just with different notation for the function name. Really, that's the only difference here in this definition, provided that limit exists. And then we can also define r prime of t to be the limit as h approaches 0 of, more generically, at all values of t for which this limit exists. We could say r of t plus h minus r of t all over h. Okay, so in thinking about what that tells us in terms of finding derivatives of vector-valued functions, we know that limits of vector-valued functions are done component by component. And so kind of looking at what we're working with here, we have a vector-valued function evaluated at t plus h, and then another vector-valued function evaluated at t, and then we're subtracting those. So when I subtract two vectors, I'll get another vector, and then I am multiplying through by 1 over h. So that's really a scalar multiplication. So this whole expression that I get is really a vector. I subtract two vectors, I get a vector, and then multiply through by a scalar, I get a vector. So we're taking a limit of a vector here. And so in a previous video, we talked about that in terms of taking the limit of a vector, we often do that component by component. So if I think about a derivative as a limit, knowing that I take limits component by component, it should not be surprising to you to find that you're going to take derivatives component by component. So you're going to just find the derivatives of each component, and then that gives you the derivative of your vector function. So that should be super easy. All right, we're going to look at a quick example here. So here I have a vector-valued function, and what we want to find here is r prime of t. So that theorem says that we're going to find r prime of t by just differentiating component by component, and then it's important to remember that your result is also going to be a vector. I'm going to use the bracket and comma notation for my answer here, but feel free to use the IJK notation as well. Okay, so in the first component here, I'm going to have the derivative of 2e to the 3t, so there's a little chain rule there. I have the 2, then times the derivative of e to the 3t is e to the 3t times the derivative of that inner function, derivative of that 3t function that's inside there. So I will simplify that to be 6e to the 3t. And then in the j component, I'm going to need to use product rule. So you can write that out, or maybe you can just write down the simplified version of the answer. So derivative of the first function with respect to t is 1 times the second function in the product here, sine t, plus the first function t, and then the derivative of the sine t is cosine t. So that's product rule on t times sine t. So simplified, I might just write that as sine t plus t cosine t. And that's all in the j component. And then in the k component, if I do the derivative as it's written, I'm probably going to use quotient rule. I'm going to just go ahead and do that. Sometimes you might want to rewrite it as t times t squared plus 1, all of that denominator to the -1 power, and then use a product and chain rule. But really it's probably easier if you can just remember to use quotient rule. So the derivative of the top times the bottom function minus the top function times the derivative of the bottom function all over that denominator squared. If I simplify that, I'll have a t squared and a minus 2t squared term and a 1 term on the numerator, so that would be 1 minus t squared. So 1 plus the quantity t squared, the quantity t squared. There we go. Okay, so in the next video we'll look at interpreting these derivatives, thinking a little bit about what these derivatives would mean.